Hello?
It's clear.
Yeah, thank you. Thank you very much. So this is nothing, this is something related with the predictive models for reliability and availability and assessment of industrial systems. So here, during the last 3 decades, this reliability has become very prominent and, has become a topic of growing interest because of its enormous application to industries. So why it has become so important is just because that, high risk systems, just I can give you an example of nuclear power plants or chemical plants and other complex industries. I mean, industrial systems, they have in different industries, which warrant highest operational safety and performability. So the system modeling, plays a very, very important role. So when you describe the system behavior over time, and it also plays a role in assessing the overall system reliability, and we can predict some of the reliability indices. So this in turn, or finally you can say, is going to help in understanding the system performance. System could be complex or simple. So normally for simple systems, we don't go for modeling. Modeling required for complex systems. So in general, if we just try to understand, because sometimes since we are coming from different disciplines, so we try to always understand that why we talk about a particular subject. So this is basically a reliability modeling. So we need to understand that how this reliability modeling and reliability basically works with it. So you see, reliability generally we define as a capability, and capability of a product or system to perform its expected job, or you can say expected function under specified conditions of use over an intended period of time. Now we need to understand this because everything lies in this, the definition of reliability, from where we try to move further and we try to see that how this modeling becomes important in this case. So when we talk about the capability, so can this capability be quantified? This is the question which we have. So yes, through probability, we can quantify this capability. So once we have the quantification, we know that how capable is our system is. Our system is. So, and then can this capability be used to compare the performance of different types of systems and take decision on their suitability? Yes, certainly the quantification helps, because if we are able to quantify, about the capabilities of different systems in operation, then definitely we will be able to compare that which particular system is better and which particular system is not suitable. Can this capability be engineered? Then finally, when we talk about the capability and we come to the conclusion that it should be more capable, then in that case, always there is a scope finally to engineer, to engineer those, to just fit in those kind of changes which you identify, while assessing the capabilities into the products or systems. So possibly, yes, so capability can be engineered into products or systems. So then the second thing, if you see here, because we are talking about the capability, so then after that, the important thing is to see, whether the system is able to perform its expected job or expected operation. So adequate operation means we just understand this way, that the failure doesn't necessarily constitute a complete cessation, or you can say that if something fails does not mean that it is the end of the operation, or does not mean that it's a complete cessation in that. So from this adequate operation, it all depends that what kind of operation we are expecting. So there are systems where we want systems to work continuously for some time, and definitely, in that case, we can define that what is actually what we mean by adequate operation. So it only means that whether the system is functioning within the bounds of its satisfactory operation or not. So it all depends, you know. So from the definition itself, we can pick up certain things which would be helpful for us to apply and to see that what we can do while modeling the complex systems. And then there is one more thing, if you see here in the reliability, that is specified conditions of use over an intended period of time. Now this becomes very important in reliability. When we talk about the specified time, it means that the duration of the mission time. So sometimes it all depends that what we are talking about. So let us say that we are talking about a communication satellite. So in this communication satellite, it's basically the mission time, if you see, it's one shot system. It means that if anything happens, I mean, while orbiting, nothing can be done at that point of time. I mean, the repair of the satellite cannot be carried out in space, of course. So here the mission time is different. You know, when we are talking about the communication satellite, the mission time is different. I mean, we have a particular expectation and we need to make sure that your system is almost 99.99% reliable. I can't say 100%, of course. So that kind of, precision is required. And another example, for example, when we are expecting the reliability from a nuclear power plant, or you can say any industrial normal complex system. So these systems are actually maintained systems. So here the mission time can be taken as the time between two annual major overhauls. So like we have a systems in industries, of course. So here the mission time exclusively depends upon the system requirement. So what you're expecting from the system. So it all depends on that. So here, when you define the reliability, you will be defining the reliability for the communication satellite in a different way, and you define the reliability for industrial systems in a different way. There, the expectation is different. Here, the expectation is different. So at the end, we are concerned with the performance of the system. So if you see in general, the entire engineering effort goes into improving the performance of the system. So when we talk about the performance, you see all these factors like quality, reliability, maintainability, safety, survivability, sustainability, dependability, all pulling together definitely will be responsible for the system to perform good. So this is the entire expectation from the system to perform in a very, very efficient way. So we have seen in the literature, thousands of maintenance models have been proposed. So some of them, I mean, if I can name, time models, degradation, degree models, cost models, shock models, inspection models, reliability and availability models, warrant models. So all these models actually, when you see the reliability, I mean, maintenance, reliability literature or maintenance literature, you will find these kind of models, So it all depends that how you are doing the modeling, so it depends, So one of the way which we have adopted for going for this kind of industrial modeling. So the thing is that, most of the time we have seen that our model worked well for industrial systems. So why it worked well is for two reasons actually. One reason that we can estimate the reliability parameters for the existing situation or existing functioning of the plant, and also it helps in predicting, for example, a particular maintenance practices have been adopted by a particular industry, and then when we use our model and we try to estimate the reliability and availability indices, we get that, and then there is some option of changing the operating condition of the existing system, for some kind of future researches, and we can also predict these reliability indices. So Basically, we will be dealing with analytical approach to represent the system, of course, by a mathematical model. And the objective is to evaluate the reliability indices from the model using some mathematical solutions. So the quantitative approach is very, very important because we'll be talking about we have talked about this quantitative, quantitative thing in the beginning. So quantitative assessment, becomes very important. So what is the purpose of this quantitative assessment of reliability through modeling? So the purpose is to assess the past performance of the system and to talk about something in the future, how you are expecting the system to behave. So it means that there are two things for which you need this quantitative assessment. One, that how it behaves in the past, how it behaved currently or in the past, and then how you're expecting it to behave. This is where you're talking about the predictive modeling. So when we talk about the assessment of the past performance, so why actually we do that? So it identifies the weak areas needing reinforcement or modifications. It establishes the chronological trend in reliability performance. It establishes the existing indices which serve as a guide for acceptable values in future reliability assessments. It enables the previous predictions to be compared with the actual operating experiences, because always, when you have something in the past and you have some indices of the past, you can always compare it with the present and then monitor the response to the system design changes. So everything what you're doing here is actually for one purpose, and that is the purpose whether things which are there in a particular industry or company is doing well or not, subject to the maintenance practices in place. Another thing is that this particular, as I mentioned in the definition itself, that future system performances also we can assess. So future system performances, or you can say predicting some of the parameters, or you can say indices based on the mathematical modeling which we do here. So what we are expecting actually out of it. So we are expecting that how the system would behave in future. Some kind of system behavior expectations in future. And then, the benefit of alternative system designs, reinforcement and expansion plans. So if any kind of design changes or alternative design system changes are required, so that would be done. And then the effect of alternative operational and maintenance policies. So whether your operational or maintenance policies need some kind of change or need some kind of improvement. So that also becomes very important here. The related cost benefit analysis. So what you are doing actually, the maintenance practices which are there in place with the system in any industry, are those maintenance practices are okay, from cost point of view, or whatever you are producing after spending a lot of money on some maintenance practices, whether is it profitable or not, whatever you are producing or whatever you are manufacturing. So that becomes very important here. So what methodology which we need to follow here? So the methodology for modeling and analysis, how we do that actually, it is for the young researchers to understand how we do that actually. So first you need to understand the way the system operates. So you need to just see that how system operates. Whatever system you have considered, you need to see that how system operates. Identify the ways in which it can fail. So you need to identify that. There are ways to find out that how system fails, and you have the existing data. Normally all big industries do have a research and development team where you can get all these kind of things. Deduce the consequences of the failures. You need to see that if something fails, not necessarily if something fails that everything goes out of control. There are certain things which when fail, you can always fix those, you can restore those failures and you can continue doing things. It depends on what kind of failures are there. Then you derive model to represent these characteristics. So here where mathematics comes into picture, and then based on that, you need to transform the actual working into the mathematical form. And then finally obtaining the reliability, system reliability measures and predictive parameters indices. Of course, when you find the reliability after using these models, then definitely there is a scope of predictive parameter, based on the varying operating condition. You can vary the operating conditions and you can get some kind of, predictive analysis. So there are many measurable reliability indices for the system which could be achieved using this approach. So the most important thing here is that you need to go for those kind of indices which really gives a very clear idea of how our system is working and what is the health of our system, I can say this way. So the important, one of the important indexes availability. So here the measuring index is steady state availability, and then reliability. So reliability can be measured in many ways. So one of the indexes mean time to first failure. It could be one of the index, mean time to failure, mean uptime, mean downtime, etc. There are many other things which you can find using this modeling technique. Capacity of repair is also one of the very, very important reliability index. And then, of course, here we will be talking about the steady state busy probability of repairment. Again, the quantification is possible, and after getting this quantification, you can very easily understand that what is the capacity of repair? I mean, how people are involved in fixing things, whether it is okay or working well or not, or need to involve some more manpower or expert to handle this. And then failure frequency, steady state failure frequency also is very important to know, that whether your system is failing quite often and what you need to do so that you improve the system performance. And finally, the profit model or the cost benefit model based on the failures and repairs encountered. So this is ultimately everyone's interest is to see that at the end what we are going to get. So profit models would be very nicely depicting all these kind of things. So what is the potential? So there are many potential applications which we could found, and we did many projects on that. So we worked for the desalination plant, we worked for the continuous casting plant, we worked for the PLCs in one of our ports, that is Salalah port. We worked with the fiber optics, we worked with the Oman cables. So we worked with Sohar aluminum, industry. So all these projects we had a couple of times, and then we got nice funding for doing these projects. And also some of our PhDs also, we could materialize from these kind of application, from these kind of industry data. So one such industrial project, which I wanted to just show you that what we have done and how we have applied our modeling for analyzing the system and for predicting some of the important parameters. Because this was the project which was a very nice project, and it was given by the Research Council here. That's why I just wanted that this I will discuss here. And then what we have done, so just a very, it would not be possible for me to talk everything, but there are many research papers which myself along with my students, we have published in all top journals. You can see I've given the reference also of those papers. So all those papers are published in some of the known reliability journals. All our Scopus and Web of Science Index journals are there. And we have done many projects also where we received nice funding to carry out this work. So also the potential application I'll take and I'll try to show you in desalination plant here. So why we have picked up desalination plant? Because desalination plant here is something very important from operational point of view, because in all these arid regions, in Gulf, normally we depend on desalination plants, and for the potable water, these desalination plant becomes very important, and their operation also, I mean, uninterrupted operation also becomes very important. So that's the reason why we have taken this anyway. So in desalination plant, you know, we try to analyze, analyze, and then some of the predictive options also we explored in order to know that how it behaves and how it is working, and are there any changes expected? You know, the current practices, current maintenance practices, are there any changes expected or something is required? So that's what we did here. And it gives a very clear idea once we get that, you know, all reliability, overall performance and everything in terms of indices. It gives a very clear idea that, you know, what changes need to be done, you know, when we address the maintenance part on such plants. So the thing is that here, as I mentioned, that normally, you know, everywhere I have seen that desalination plants are, you know, being used for the water supply, and that's the reason why we need its continuous operation, you know, and if we see, so what we have done here, that from the desalination plant we collected 7 years of maintenance data, which talks about the complete record, that what they have, I mean, spent and what kind of maintenance practices they adopted. So from the data, we try to extract the rate of failure of different evaporators, because in this plant, what we found, there are 7 evaporators, and all those 7 evaporators, out of those 7 evaporators, 1 evaporator they used to keep as a standby, and 6 used to be in continuous operation. Because sometimes when any of the evaporator goes out of order, then definitely the standby takes the place of that you know, failed evaporator, and then it continues in the same way, and because they cannot afford to lose, you know, any kind of production. So that's the reason why they keep one particular evaporator always in standby mode. So from those data, we try to extract some, you know, some rates of failures, rates of repair, rates of replacement, reconditioning, reinstallation of some softwares because of which some problem occurred, because we saw those things also in the data. And then different costs for repair, replacement, reconditioning, reinstallment. So all these things we estimated from the data. So data summary, if I'm able to show you, it is very clear that, you know, we expected these you know, these things from the data. So estimated rate of failure is there with us, and then rate of maintenance is there with us, a rate of shutting down of the plant. So normally once in a year during season, they shut down the plant for 1 month and to carry out the complete overhaul of the plant. Because during winter season, the you know, water requirement goes down, and during summer season, they cannot afford to shut down the plant. So during summer season, it continues its operation with all the 6 evaporators, keeping one as standby. And then all these repair costs also we could estimate, and all other estimated costs which we are seeing here, you know, in terms of the revenue, in terms of the expenses. So this C0, C1, C2, C3, C4, you can see at the end when I'll be using the profit model evaluate the profit. So the plant is actually analyzed for different operational situations. So here I have used the term semi-Markov processes and regenerative point technique. So the people who are not coming from this background possibly will find it a little difficult to understand the semi-Markov process and regenerative point technique. Just to give you just an idea, this is one way which we adopt while doing such analysis. And as far as it's detailed, what it is, semi-Markov process and regenerative point technique, that detail can be seen in some of my research papers. So the idea is that regenerative point technique, why we are saying, because when we do any repair, so the system works as good as new. This is what we are actually considering here. So four reliability models have been developed here, and then relevant reliability indicators are obtained. So one model which we have developed is the same what we observed there, and other three models are for the prediction purposes. Sorry. So now the measures of plant effectiveness, or what, as I have mentioned there in reliability, we can go for mean time to system failure. It tells you that what is the quantification, I mean, what quantity you have arrived, at the end of the day. I mean, how after 4 years or after 3 years or after 2 years, what was the mean time, when during which the system or the industrial, any unit was available for profit. I mean, how much time it was available for working or operation. So this will give you a mean time, to system failure. So this is one of the quantification. The operation time, you can say, until it fails completely, or when it fails, then again you repaired or restored, and then again it started working. So all those collecting together, you can take it as an average, and it gives you the mean time to system failure. Plant availability is one of the very important index. Expected busy period for maintenance, I mean, for how much time the maintenance carried out, and same thing for busy period, that is the the capability or the capacity of the people who are involved in fixing those problems, or you can say maintenance practices, those who carry out. And then expected busy period during shutdowns, and then expected number of repairable failures, and then finally cost benefit analysis of the system. So this is what we have tried actually to achieve. And here, if you see, so we have developed for this particular desalination plant 4 models. So one is portraying the actual situation of the plant. So there are 7 evaporators. You can see there are 7 evaporators, and shutting down during winter season for 1 month, and repair and maintenance being carried out on first come first serve basis. And 6 of the evaporators are in operation, while 1 is always under scheduled maintenance and used as a standby. So here, if you see, the important thing which we have seen in the data, that there is no priority for repair and maintenance. I mean, whatever comes first, for example, any component or anything goes out of order, that is to be fixed first, and then normal maintenance, or repair, whatever comes first. So that will be the objective of the maintenance team is to fix that first, whatever comes first. So they take up that, and then start working in bringing the system back to operation. So all data talked about this particular thing which is written here. 6 evaporators with first come first serve basis. So based on this, we try to develop the model. And then the second model, which you are seeing on the right side. So this is one of the variation which we have done to this particular existing practice, and we tried to see that I mean if we make these changes, then how it is going to affect our reliability indices at the end. So here, if you see here, the model which we have developed analyzes the plant with priority for repair over maintenance. Now here we are giving priority, to repair over maintenance. I mean, in the previous case, this is not the situation. There whatever comes first, we are fixing that. Here we are giving priority for repair over maintenance, because sometimes what happens for a particular type of repair, we need to call some experts from outside, and they are not every time appointed there. Only when it is malfunctioned or when it goes out of operation, then they call and they come. So when they come, so they take little time in bringing the system back to operation. So that is the reason why, from probabilistic angle, it becomes important to understand the pros and cons of different, different operations, and that's the reason why we vary the operating conditions. And third model is also for the predictive, and this is based on variation. And here we added some of the inspection time also, and just we try to see that if the regular inspections are being carried out instead of just inspecting when it got failed, if regular inspection is carried out, how it's going to affect the operation, of course. And then we try to just put some of the inspection rate into that and try to see that how it happened. I mean, how it started working. I mean, what is the final outcome? Is there any major difference between the outcomes or not? And then finally, again, we try to break down the repairs into two categories, minor and major. And the reason again is very simple, because again, minor repair means someone can fix who is at the level of foreman or technician or whosoever he or she is with the system. But when it is major repair, then possibly again you need to call someone, those people who installed in the beginning those systems. So again, here also, minor and major plays a role, because of the time duration which we need to fix the minor and to fix the major. So we try to again differentiate these two things and just try to see that if this thing happens over the scheduled maintenance, what is the final outcome in terms of the reliability indices. So it is important here, that we need to assume certain things when we do modeling. Now, the question is that why we assume, I mean, what is the benefit of assuming that? So the answer is very simple, that, when you don't have any way to find or to see that which particular, because everything has got a pattern. Repair has got a pattern, failure has got a pattern. When you see the data, you will find in 4 years or 5 years of time, there is a pattern. So what is that pattern which it follows? So that is most important thing to see. And that pattern is described by the distribution. So it is important for us to see that which particular probability distribution is to be used. Now, as a customary, you can say, over the years we have been seeing all failure times of the components or units, they assume to be a failure and to be an exponential distribution. Why? Because normally we have seen that exponential distribution fits well. Now, the problem, there are many distributions which we can fit into the data. So how do we decide? So the new thing which we have started doing now to the existing modeling is to started using some of the new softwares, which are there in place. And those softwares are very useful, because as I told you, while fitting the distribution, because when you are talking about the data, it means the important thing for you is to talk about the pattern. And once you know the pattern, then only you can decide that what is the probability distribution it is following. And when you know the probability distribution, when you are able to fit in properly that probability distribution, then it becomes easy for you to evaluate the other indices, other parameters. So that's the reason it becomes important for us to know that which particular lifetime distribution. There are many lifetime distributions, exponential distribution, gamma, Lane-Blay distribution, Weber distribution, sometimes Rayleigh, and then there are many generalizations of these distributions. So that becomes important for us to excuse me please, to see that which particular distribution fits well to the data. So what we have started doing now, we have started using easy fit or fit list to decide, and started comparing the goodness of fit for the appropriate distribution. And once we come to the conclusion that this is the distribution which fits well to the data which we have with us, we use that distribution. And because of doing that, the possibility of getting much deviated outcome becomes minimum. So when we use, this is something new which we are doing now. We have started doing, we are first coming to the conclusion that which particular distribution fits well to our data, so that particular distribution we use. And as I mentioned, the deviation from the expected values will be less in order to reduce the error, you can say. So if we use any of that, like here I have used easy fit, and I found that some of the distributions for a particular set of data, so you can see log normal is fitting well, and then Webel, and then exponential, and then gamma, and then Rayleigh, and then Erlang. So based on this, we can decide that which particular distribution. So in our case, exponential did well. So this is the model you can see, which is the actual situation at the desalination plant. So you are seeing here, this is the state. So all this particular representation is nothing but it is the transition states, of the system which it behaved, in which it behaves, and all these things we gathered from the data. So let us say that in the beginning, if from probabilistic angle, if we try to explain this, if we try to understand this from probabilistic angle, you see at the state 0 there are 6 evaporators, and one is under maintenance every time. So as I mentioned that there are 7 evaporators at the industry, and one is always as a standby. And of course, when I say UMS means, if for example in a particular season, if we are talking about, so let us talk about the summer when the water requirement is more. So that time one evaporator is always under maintenance, and we keep this as standby, and 6 are operative. So from here you are seeing from 0 state it is moving to 1 state. And what is happening at the state 1, because here you see you are seeing beta 1 here. Beta 1 represents the rate of unit moving from summer to winter, and then it has come to 6 operative, and then under maintenance before winter. So here you see it is going from one state to other state. And then from 0 it can go to 2, where 1 unit fails out of these 6 which are operative. For example, we are just considering it as a unit. It fails, and there are now 5 evaporators operative, and the failed is under repair, and then maintenance is also there. So what we do immediately this maintenance, where the maintenance was carried out, it is fixed, and then whatever is failed, so this under maintenance evaporator will take place, will take the place of the failed one. So again, you see there are now 6 evaporators, and now this is FRS, which is that the failed evaporator is under maintenance now, under repair now. And then, GMT you are seeing here. So GMT is the probability density function of maintenance rate. So this we have got from the, from the data. And then, if you see that all these possible states are there from 1 to 3, where the complete shutdown of the plant is there. And then once this overhaul is done, then it is brought back. And then from here, you are seeing for different states, all possible states we have explored in this particular model, where where we depicted the situations which we observed there in the data. And then, usually, using the conventional mathematical way of doing this modeling, and then using the differential equations and transforms and many other things like that, recursive relations are framed. And we found, so how we framed that just in the next slide I will be able to show you. But when we do that particular exercise, when we do all that modeling, what we found here, the mean time to system failure, here we found that 256 days, the system worked nicely. And then availability, we got 98.62%, is the availability value, and the profit is there, 603 per unit. So this is in Omani Real uptime. So these just I have given this particular, these only 3 indices just to show you the difference, that what difference we got between the modeling, between the 2 models. So this is the actual situation which we have seen. And then if you see, and there are many papers available on this, you can very easily understand the new researchers I'm talking about. You can understand, in much detail we write in journal papers that how we are doing this and how we are framing the recursive relations to form the equations. So this is another situation. So here you see when it was there at the industry, whatever was there, which was happening, which was the actual situation which we observed. Based on that, when we obtained the reliability indices, we found 256 days MTSA, whereas in this case you see it got reduced 134 days, and availability also reduced. It means that there is no use now in order to go for any kind of change into the maintenance practices which are there. And then after that, third model shows you 134 days, but the availability has increased now here. So it is up to the engineers, plant engineers, to decide that which is to be considered, whether they're able to afford the availability, or they're losing the availability, or they're able to afford the increasing the mean time to system failure. Because availability talks about the probability that in future, when you expect some system to operate successfully, will you be able to get that? So that is the quantification for availability. And then profit also, 596 here, whereas here you are seeing that it is 603. So it means that their existing practices were fine. So when we talk about the prediction, so now here we are observing whatever is there with the system, and then here with those changes we are trying to predict that what would happen if we make these changes. So there are 4 models which we have developed, and very easily we can compare that which particular practice which they are actually using, because this modeling transition states you are seeing will also change when they change the maintenance practice. So based on that, you are getting the final outcome. Sorry if I'm going out of time, but just I will try to finish very fast. Do I have 10 minutes more, please? So these are the transition probability and time, and as I mentioned that these transition probabilities, we can see how these transition probabilities are formed in our research papers. I have given a detailed list of the research papers. and then you keep doing that, and then find the transition probabilities. And actually this P00, P01 is the quantification of those transition probabilities. How much? So let us say that P00 something, you have got 0.001 based on the data. So this is how, you see. And then, how to verify whether we are going right or not. So from a particular state, you are seeing that the possibilities are P00, P01, P02. So from a particular state, possible movement from a particular state. So all the possible movements from a particular state, the sum should come out to be 1, which establishes that we are going in the right direction. And then we try to evaluate the mean SOJOURN time also. And this is a very standard formula for mean SOJOURN time. And, for different states, we can calculate that mean SOJOURN time by using this usual formula. This is the probability formula, the probability that, how much time, what is the probability that the system will stay in a particular state, for example, at state 0 or at state 1 or at state 4 or any other state, how much time the system spends. So this is another quantification, of those of the probabilities. And then we evaluate the mean time to system failure. So as I told you, the expected time for which the system is in operation before it completely fails. This is another quantification. So if MTSF is more, means the reliability is better. So these equations are framed. These are called the recursive relations. And as I mentioned that, if you refer some of our papers, you will get the detailed, form of framing these equations. So this you can see, it's a normal recursive relation. The people who are aware of, these kind of equations where we are talking about the cumulative distribution function of the first passage time from any regenerative state I to a failed state J. So regenerative state I means the state from where system works like new. Once the system is repaired or restored to a failed state. So all those recursive relations, we can calculate here from different states. And then finally, we can get this quantification of mean time to system failure, which you have seen in different models. I have mentioned that. And then you can find the plant availability, and you can find definitely the system, the probability of the system to operate within the given tolerances at a given instant of time. So given instant of time means it is something which is related to the availability. So availability index will tell this that the system, what is the probability that the system will be able to operate within the tolerances at a given instant of time. So in future, we will be interested whether the system will be available for profit or not. So this particular quantification gives you that particular index. And then this is the normal, usual, conventional way of framing recursive relations from different states, operating states, which you have seen in the figure. So there are 11 states. So for all 11 states, we have framed the equations using conventional way. And then this is convolution, which we are using between just wrapping the two distributions. So this is the convolution which we have used. And as I mentioned, that detail you can see in our papers. And then you can take the Laplace transform for all these equations. For taking Laplace transform and then for solving, you can use some software because you might get many states. For example, maybe 30-40 states. For 30-40 states mean 30-40 equations, big equations you will get. So it is always better to handle these equations for getting the solutions, using some software. So you can use Mathematica, you can use MATLAB, you can use anything. So finally, the steady state availability of the system we will be getting by the usual conventional formula. And then you can similarly, measure, other system effectiveness. For example, busy period analysis for maintenance, you can find busy period analysis for repair, you can find expected busy period during shutdown, you can find expected number of repairs, you can find everything you can find using the a conventional approach of framing equations and using the concept of differential equation, Laplace transform, etc. So using the data summary which I have shown you before, expressions for reliability we found, so mean time to evaporator, we have got this, availability, we have got this, expected busy period, we have got this, and likewise profit, we have got this. So we can obtain these indices for other three models. So this particular thing is what is there with us, with the industry. Other three models are the variations to the existing system, or you can say to the maintenance practices because of which you are getting this. So prediction comes for other three models. So that is how you are then at the end, you can calculate the profit model. I mean, you can use the profit model to calculate the profit, to get the profit. And here, the profit model, as you can see, what you call as a profit. The profit is expected revenue and then the expected total cost within a particular time period. So, so let us say that, we have, as a maintenance practice, we have, for example, the maintenance for repairing the failed unit, or you can say the overall maintenance, or you can say the maintenance during shutdown, or you can say the replacement. So all these kind of things require cost. So those costs, when we multiply by the total fraction of time for which a particular person is busy in fixing those problems, that gives another quantification, and that quantification goes for the total cost which you have spent or which you are spending there. And then revenue we get from the availability. I mean, during the time system is operating, when system is working, you get the revenue. So from the revenue, that is what I have written here, C naught, A naught talks about the revenue part, and then minus all these things, whether you are busy in fixing the maintenances, or you are busy in fixing the repairs, or you are busy in fixing the software part, or you are busy in fixing the replacements. So all those things involve cost, so we can subtract from that to get the profit. So for all the models we can do this, and we will be able to get that what is the difference between the profits and ultimate, the objective of going for some kind of prediction. So we can have different, plots which tells us about the marginal revenue also, for example, below which you can't go. And if you're going below that particular value, so definitely there is no profit, means you can very easily say that a particular maintenance practice is not suiting well, and you can go for some kind of changes or improvements. So many graphs you can see for cutoff points, just to see that what is the margin, with which you can operate for getting, getting a proper revenue, or you can say the expected revenue from a particular plant or industry, whatever it is. So in conclusion, I can say that the model offers a scientific basis through which the possible key downtime risk factors of the plant could be gauged. Reliability indices of the system are estimated and predicted by changing the operating conditions. This entire process helps in understanding the overall system effectiveness in any industry. Cost benefit analysis, you can go for using different models. The company can decide, or industry can decide through the comparative analysis among the models as to which and when a particular model is suitable for implementation. Through graphs, you can establish some cutoff points, which will be very helpful for you to get a glimpse of the marginal revenue, what is actually that optimum product cost, which becomes responsible for marginal revenue. And then, as far as the future development is concerned, this is the most important thing which I always put a lot of emphasis on this. And I would like to mention here that we need to go for now some new maintenance models, So where we can talk about some kind of probability in fuzzy or bake set theory. Uh, so, and definitely these things would help us in extending the range of theoretical application to industries. The best fit lifetime distribution can be picked up using available softwares. Recently, we have seen many softwares, which tells us very clearly that which particular lifetime distribution is best fitting. And once we do that, as I mentioned, we will be reducing the margin of error in our final values. So this is another thing which we have to do now in our work. And then some new distributions and new stochastic processes we need now. Our new researchers should look for some new distributions now, and in order to add, or in order to go for some kind of added value to the existing practices. New algorithms, can also be thought of, because now we need quick solutions. And definitely once you have model in place, very easily and nicely you can develop, the new algorithms or quick solutions. Application of statistical inference also is something which is missing currently, and that also we can see, because statistical work can correct maintenance models. So such as you can say robustness, goodness of fit test, and model selection, based on real data. So simulation techniques could be useful. So people are doing simulation, but still some more is required in that. And this is what I thought that I will share with you. And we have done many projects on this kind of modeling practice, and it has strengthened our research facilities also. So anyway, and these are the references which I have always been referring to, and some of our very good publications in top journals, for our all work which we have done over the years. Anyway, thank you very much from my side. I'll be very happy to answer any question.
Yes, Professor. I have one question, basic question from you. Can you hear me?
Yes, Dr. Shahzad.
Yes. Is it practically possible that reliability for any model can be equal to 100%?
We all know that nothing in this world can be 100%. Only what we can do, we can reduce the error factor. You can say, you can talk about 3 sigma, 4 sigma, 5 sigma. So currently, people are just working with 99.9999. So if I say this means it is almost, you can say, but we cannot call that 100%. Nothing is possible to get 100%. Only our endeavor is to reduce the amount of deviation from the actual 100% to the value what we get.
Okay, thank you. I have one more simple question, that can this reliability we can implement for any COVID model in order to forecast?
Yes, Dr. Shehzad, we have actually used some of the methodology, not exactly reliability, but we have done some analysis for COVID cases. We collected almost 300 COVID patients, where we analyzed the pre-symptoms, post-symptoms, and during during that period of COVID, how patients they had undergone the problems. So this particular analysis we did, but it doesn't have to be, we don't have to use this particular modeling. Normal analysis would work well in order to understand that how the post and pre symptoms were there, and how then after that, how after that we observed some changes in the patients. So that we have done with normal, our normal statistical analysis we did, and we could do that. So no need to go for any modeling. Possibly there is a possibility, but I have not explored that.
Okay, thank you. That is all from my side.
Thank you.